Okay, so the purpose of this video is to take it to the next step. Now that we know how to factor higher degree polynomials, we want to take a look at how we can use that factoring to do a little bit more. And in essence, what we're really going to be doing is solving these higher degree polynomials. So if you take a look at the learning goal at the top, I've actually written that a different way. I didn't just say solve higher degree polynomials. I stated it a little differently because this is typically how it's referred to. We say that we're going to find the zeros of a higher degree polynomial, or sometimes you'll hear a different phrase. They'll say find the roots of a higher degree polynomial. But in essence, what we're really doing is trying to find all of the solutions when we set the expression equal to 0. Right? So if you take a look at this statement here, what I'm basically telling you is exactly that. To find the roots, or to find the zeros of higher degree polynomials, you are going to use factoring and everything that you know about factoring, and you're going to use division and everything that we've learned about long division and synthetic division to take a big higher degree polynomial and write it as the product of linear, which means highest exponent of 1, and quadratic, highest exponent of 2 expressions. Right? So we should get, in the end, something that pretty much looks like, okay, let's see, say an example, so maybe something that looks like x plus 1, x plus 2 squared, x squared minus 3. So something like this, right? This is a linear expression, x plus 2 is a linear expression, x squared minus 3 is a quadratic expression. What the claim is, and there's something called the fundamental theorem of algebra that basically says that you can take any polynomial and write it in this form. And so we're going to use what we know to do that. Okay? After we have each of these expressions from whatever polynomial we started with, we're going to set each of these equal to 0 and solve them using everything we know about solving polynomials up until now. So let's take a look at some pretty straightforward examples that use factoring, and then in the next video we'll take a look at some things that maybe do not use factoring, where we have to use some long division. Okay, so here's your first example. I'm asking you to find all the zeros of 21x cubed minus 77x squared minus 28x. So again, the idea is we're going to factor this as much as we can, right? So in this case, I would take a look and say 21, 77, and 28 all have a 7 in them, and there is an x that is common as well, right? And then it looks like what I'm left over with is 3x squared minus 11x minus 4, okay? And then on this trinomial that's left over, I'm going to have to do an AC factor. So if I say AC is negative 12, B is negative 11. It looks like negative 12 and 1 will multiply to negative 12 and add up to negative 11. So let's use that. So I'm going to say 3x squared minus 12x plus 1x minus 4. My first group has a 3x in common, and that leaves behind an x minus 4. My second group, these two expressions just have a 1 in common, and they also leave behind an x minus 4. So the AC factor on this trinomial turns out to be 3x plus 1 and x minus 4. And again, we're not going to forget that all the way down, 7x was sitting out front, right? We're just not writing it for simplicity. Okay, so at the end, I would say the factored version, completely factored, if you notice, linear expression, linear expression, linear expression. That means I'm done. So I'm going to say each of these factors should be set equal to 0. So let's do that. 7x equals 0, 3x plus 1 equals 0, x minus 4 equals 0. So here's the final answer to their problem. Find all the zeros of this expression. Okay, well, I'm going to say when I divide 7 on both sides, I get 0 as a possibility. When I subtract 1 and divide by 3, I get negative 1/3 as a possibility. And in my last factor, I will get 4. Right? So I'm actually claiming that there are 3 zeros of this expression, or 3 roots of this expression: 0, negative 1/3, and 4. Okay, and here's a nice little trick for you. Okay, every single time we find the zeros of an expression, this number right here, the highest exponent that you see, which is called the degree of the polynomial, this is a degree 3 polynomial, and if you notice, I have 1, 2, 3 zeros at the end. That will always happen. Okay, and there's some little tricks and things that we'll look at as far as that 3 matching the exponent, but we'll see those as we go. Okay, here's a second example. So same basic idea. I see a 4 is in common. I see that there is a 2 in common with all these expressions, so I'll say 2. And I see that there's an x squared in common. Okay, after I remove that, it looks like, again, 2x squared minus 9x plus 6. Okay, so I'm going to look for numbers that multiply to 12, okay, and those same numbers have to add up to negative 9. Right, so I'm looking for the same thing. So I'm going to say, okay, numbers that multiply to 12 and add up to 9. Well, if I list the factors of 12, because I'm thinking about those and I can't find any, here they are. Find numbers that add or subtract to 9. If you take a look at this list, there aren't any. Okay, so we actually have ourselves a situation here. We're trying to factor using AC factoring this expression, and we can't. Okay, so I'm moving all this stuff out of the way. Okay, it's because we're going to have to do a little bit more work. In order to find the answers, right, this is as factored as I can go. I'm going to get rid of our little AC over thing here. I'm basically saying I've factored this into two quadratics. That's as far as this factors, which means that either 2x squared equals 0 or 2x squared minus 9x plus 6 equals 0. I can't factor this trinomial anymore. We just tried and it doesn't exist. So guess what? We have to use the quadratic formula on this second expression. Okay? So there are going to be times where some of the expressions are not factorable. We have other ways of solving that quadratic. If you take a look at what we wrote here, we said set up each of these factors and equal to 0 and solve. Okay, so they're not always going to factor. And in this case, the first one's pretty easy. I can say that 2x squared, or I'm sorry, that x squared equals 0. Right? If I divide both sides by 2, let me get rid of my 2 here. If I divide both sides by 2, I get that x squared equals 0. And when I square root both sides, x is still 0, right? So 0 is a solution. It's a root to this expression. The other one, I'm going to have to actually do the quadratic formula. 9 plus or minus, and again, I'll do my b squared minus 4ac. This is negative 9 squared minus 4 times 2 times 6. Okay? That looks like 81 minus 48. Okay, 81 minus 48 is going to be 30. Let's see if I can do this right. 81 minus 48 would be 33. Okay, and then I'm going to put that all over 2a. Well, my a in this case is the 2, right? In fact, I'm solving this. So 2a would be 2 times 2 is 4. Okay, so I'm going to say these are my two answers, right? They're not nice. 9 plus or minus the square root of 33 over 4 is one of my solutions. We can get decimal approximations for those if we'd like, right? So we can kind of figure out what the numbers are. So if I do 9 plus the square root of 33, okay, 9 plus the square root of 33 is about 14.7 divided by 4. This one comes out to be about 3.69, okay? And if I do the same thing, okay, I'm going to do my calculator off to the side here. 9 minus the square root of 33. Get my answer. And divide that by 4. I also get about a 0.81. Okay? Or 0.81. Right? So I'm actually getting two solutions. Right? 3.69 is 9 plus the square root of 33 over 4. And 0.81 is 9 minus the square root of 33 over 4. So I get one answer, two answers, and 0 is my third answer. So there are going to be times where when you try to factor, it does not factor nicely. We do know how to solve problems that do not factor nicely. Okay, so let's take a look at two more examples. Okay, this one is going to be finding all the zeros. Okay, well, to factor this, I'm going to just use the grouping method. So I see an x squared in common, okay, and that leaves me with x minus 3. And in this group right here, it looks like I see a negative 25 in common, and that also leaves me with an x minus 3. And then I can say x squared minus 25 is a factor, and x minus 3 is a factor. But I'm not done. X squared minus 25 can be factored one more time. X plus 5 and x minus 5. Okay? And then that x minus 3. So I'm going to set each of these equal to 0. So it looks like I'm going to get x plus 5 equals 0, x minus 5 equals 0, and x minus 3 equals 0. So I get negative 5, 5, and 3. And again, if you notice, highest exponent of 3, 1, 2, 3 answers. That works out good. All right, last one. Okay, here's my expression. I see 4 terms, so I'm going to try grouping again. Let's see what happens. Okay, first group looks like it has an x cubed in common. Okay, and that leaves me with x minus 2, Okay, and this group right here has an 8 in common, and that leaves me with an x minus 2. Okay, oh, I'm going to have to fix something. We're going to make this one minus so it works. That should be minus 16. Okay, so if I do that correctly now, okay, x cubed plus 8 and x minus 2. Okay, so let's say this now turns into x cubed plus 8. Those are the numbers on the outside. X minus 2. Those are the numbers on the inside. Okay, and if you remember what I said is we can factor something into the the product of a bunch of squareds and linear factors. This is not a squared or a linear factor. So we actually have to factor this again, and if you notice, I'm going to do this off to the side again so it doesn't get into our work. This is x cubed plus 8, okay, is the sum of two cubes. This is x cubed plus 8 cubed. 2 cubed equals 8, okay? X cubed plus 2 cubed. So we claimed in a previous video that this can be factored into x plus 3, x plus 2, okay? And you might have to go back and look at your formula on this, okay? X squared minus 2 times 2 times x plus 2 squared, okay? So if I go through and simplify this, I get x plus 2, I get x squared minus 4x, and I get a plus 4, okay? So I'm taking a look at this and I'm saying, okay, x plus 2, and oh, wait a second, this one right here can be factored again. So I'm going to bring all this over so we can see it. This x cubed plus 8 is really this expression using the sum of cubes rule. So I'm going to say this is x plus 2, okay, x squared minus 4x plus 4, and x minus 2. Okay, so again, we have to look at this trinomial and say, can we factor this again? And in fact, we can. This turns into x minus 2 and x minus 2, right? This is negative 2 times negative 2. Negative 4 is negative 2 plus negative 2, right? The other stuff is just going to come down. So if you notice what happens here, something strange happens. Okay, I end up with 4 factors, which I should have had, right? 4 different zeros, because my highest exponent is 4. However, 3 of them are the exact same thing, so I don't need to repeat those 3 factors, right? So I'm going to write this another way. I'm going to say this is really x plus 2 times x minus 2 to the third power, right? X minus 2 times x minus 2 times x minus 2 is x minus 2 to the third power. This is the factored version of what I started with, but I only need to set each of these linear expressions equal to 0 one time. I don't need to set a repeating x minus 2 equal to 0. I'm just going to get the same answer over and over again. So I can say x is equal to negative 2 and x is equal to positive 2 are my zeros. Okay? And if you notice, this is only really 2 zeros with a highest exponent of 4 up top, and that is because when we factored it, I had repeating zeros, right? These repeating zeros, these repeating factors are something called a multiplicity, which is something that we'll discuss later when we do graphing, but it's entirely possible that you will only have 2 unique factors, okay, even though there were 2 unique zeros, even though there were 4 factors when we originally started.